wave motion. So last week we started the lesson waves, right? So in that session we discuss about what is a wave, right? Actually, what is a wave and what are the wave types? Remember that, right? How we categorize waves according to the nature of the disturbance. How we categorize waves mainly into three types. According to the nature of the disturbance. If the disturbance is mechanical, those waves are mechanical waves. They produce due to the mechanical disturbances in media. Then the other type, the second type of wave, is electromagnetic waves. Time varying electric and magnetic fields produce electromagnetic waves. Right? Then the third one is matter waves. Right? Tiny particles like protons, electrons, the moving particles, they associate with a wave called matter wave. Right? So we talk about de Broglie wavelength, those are the things, right? So let's go back again to the earlier part. So what is a wave? And what is a wave? Wave is the method of energy transfer without without the movement of the particles. Particles move in but they oscillate, but they doesn't move. They oscillate, right? Actually, it is a sequence of oscillations makes a wave propagate through a medium, right? So after that, we did discuss about mechanical waves. Under mechanical waves, there are two types of mechanical waves we discuss. Okay, like what are those two types? Transverse and longitudinal waves. So what is a transverse wave? What is the key feature of transverse wave? How we categorize these waves as transverse and longitudinal? What is the fine line? Direction of the movement of the particle. Right? In a transverse wave, particle moves perpendicular to the direction of wave propagates. Right? In longitudinal waves, particle oscillates or moves parallel to the direction of wave. Right? So what are the examples of transverse waves? Give me an example. No, sound waves are not transverse. Water waves, right? Surface water waves, and what is? Waves formed in a string. Seismic waves like secondary waves, right? Those are transverse waves. And what are longitudinal waves? Examples: sound waves is the most famous longitudinal wave, right? In transverse wave, what are the when a transverse wave propagates through a medium, what can you see? What are things you can see when the shape of the wave moves in a medium? What are the special points you can see? Crest and troughs. අපි ගැන කතා කරාද නෝ? දැන් තාවද? Transverse waves අපි discuss කරාද? No. එහෙනම් මම මේ further ඉස්සරහට එන්න වැඩක් කියන්නේ. Right. තොතත් අපි නේද matter waves only නේද? Right. So then we need to go to the two types of mechanical waves. There are two types of mechanical waves. Right? According to the direction of particle movement, we categorize those two kind of waves, transverse and longitudinal. Right? So in a transverse wave, right? Transverse waves. Right, in a transverse wave, so this is the key factor. So suppose this is the direction of propagation of the wave And particles in the media, they oscillate normal to the direction of propagation. So these are the particles, they oscillate perpendicular to the direction of the wave propagates. Right. So this is the direction of particle movement. Right. So this arrow represents the direction of wave right. So this is the direction of particle movement, right? And wherever transverse wave is propagate or is moving in a media, so we can see a wave form like this. Suppose this is the equilibrium positions of the particles. So we can see this kind of a graphical shape. Right. When we have a shape here, try to memorize a water surface water wave. Right? When water wave traveling on a water surface moves like this. Right. Yeah. So these are peaks. At these points, what can you say about the displacement of the particles? These points, they are maximum. They are in the maximum displacement. Right? Those points are called crest. Right? So at these points, the displacement of the particles are minimum. These are troughs. Right? So you can see clearly crest and troughs. In English we say sheath and Newton. When transverse wave travels in a medium, you can easily see the crest and troughs there. Right? Right? Okay. Then, so the length between two adjacent crests, or the length between two adjacent troughs. The length here, but this length, right? Length this is special. Length between two adjacent crests, or the distance between two adjacent troughs. This length is called wavelength of the transverse wave. So it is the wavelength of the transverse wave. Wavelength. If someone asks from you, what is the wavelength of a transverse wave? How you define it? The distance between two adjacent troughs or two adjacent crests is a wavelength. Right? It's a wavelength. Okay, so remember at this position, at these troughs and crests, right here, the particles are at maximum displacement. Remember, these particles execute simple harmonic motion. They oscillate like this. So what can you say about the, what can you tell about the velocities of particles at crest and troughs? Right? Try to think through the simple harmonic motion. These particles are undergo simple harmonic motion. Now these particles are at its maximum displacement. What can you say about the velocities of particles at crest and troughs? Is it maximum? Where's the velocity maximum in simple harmonic motion? Where? At the center of oscillation. At capital O. Where is the center of oscillation of this movement? Here. Right? Particles, whenever the particle passes this point, it has a maximum. And here, they are instantaneous rest. the velocities are zero. Right? At the peaks or at the crests or troughs, particles at crests or troughs, they are instantaneous rest. Remember the MCQs will have. They are at instantaneous rest. Kshanika nishratavi. Right? Okay. Then, so what are the examples for transverse waves? I have repeat karagam. What are the examples? One is surface water waves. Right? We cannot say all the water waves are transverse. Waves in sometimes longitudinal waves also transfer or travel through water or liquids. That's what longitudinal waves and the water. But on the surface of a water surface wave, only transverse waves can propagate or traverse on the surface of a water. Right? So surface water waves are transverse. What else? Waves forms in a string. The guitar string, maybe violin string, string. So waves forms in a string also transverse. Then what else? Seismic waves come to another. Secondary waves, they are transverse waves. There are a number of examples we can give for the transverse waves, right? So wave pattern can be easily seen where transverse wave travels in a medium. Then, make an introduction diagram, we need to draw some graphs after this. So therefore, we need to write a brief introduction about transverse waves. I put the topic mechanical waves. Yes, now I guess it's in there again. But it's okay on. mechanical waves. Yeah. There are two types of mechanical waves. Hello, mechanical waves. Like that's okay. Okay. Start catching the mechanism, right? Under mechanical waves, there are two types of mechanical waves. There are two types of mechanical waves. First one, transverse waves. Transverse waves. Transverse waves. Take a look at it. Come on, right? And second one is longitudinal waves. Now, come on, I'm going to walk around. Stop. Initially, I'm going to make that. I think about it. I'm not taking a case of the come on. That's right. Right. Then you have to tell them. Right. So now let's start with transverse waves, right? Now take a part of it. Take a part of it. We get a transverse waves. You make hard to relate to a part. Right. Now the topic is transverse waves. Like subtopic. Topic is transverse waves. Transverse waves. Right? Right under it. In a transverse wave, particles in the medium vibrates direction perpendicular to the wave propagates. The wave propagates. Right. So draw this. Right, I am. Take that. Right? Right. Then examples. Examples for transverse waves. This one only. Right? This figure only. Like examples, like an example of a transverse wave. Surface water waves. Surface water waves. Surface water waves. Surface water waves. Then waves on stretched waves on a stretched rope. Stretched rope. Seismic waves, seismic waves dash in front of S waves or secondary waves. Seismic waves is dash secondary waves. Not all these seismic waves are transverse, right? Only secondary waves, or we say S waves are transverse. S waves are transverse. Right. Then put a star mark and right. When the transverse wave travels in a medium, at some points, the displacement at some points, the displacements of the particles get maximum, and at some points, the displacement of the particles are get minimum. The points where the displacements are maximum. Displacements are maximum for crest. Where the points the displacement are minimum forward. Where the points displacement are minimum forward drops. Right. So you can draw this wave pattern and name the points where the crest and troughs are. So draw this figure and name it. Right, hurry up. Right. Right on the figure. And particles are at particles are at particles at what is I? Crests and troughs. Particles, crests and troughs are at the particles are in crest and troughs are at instantaneous rest. Particles are in crest and troughs are at instantaneous rest, which means the velocity is zero. At the moment, right, whenever the particles are at the highest point of its motion, the velocity is zero. Right? So when this particle, right, does this particle remain at this point for forever? No. Right? So after right, after a short while, so what is the shape of this wave? Right? Here, this is important. Right? After a very small time period, so this is the shape of the wave now, right? So I'm going to draw the shape of the wave after a delta t time. Right. So this particle at here goes down. So this is the this is the so this is the wave after a little bit of time period, right? That the first instant when we observe the wave is at here, right? Suppose at the time capital T equals simple T, right? So waves at here. So this is belongs to when the wave now have traveled extra time, delta T time. So what can you say about the particle motion? Like whether in particles direction of motion, how can you recognize that? May whether in passing again the way the particles, koi pathwala within your move when they are there. You can get an idea from this wave, right? So suppose, right? So in this area, particles in this area or this, this area. So what are the direction of motion just after this position? Right? Now this moment, the particles are here. But right after that, what is the directions of particles? They try to move up or down. Yeah. And particles at this region, they try to go down. Right? Up to here. Then particles at this side, what is the direction of these particles? They try to go up. Right? Particle at here, it tries to go up. So this is some of the motion of the particles. Right? Up to this point. All these particles up to this point. Particle at here also try to goes up. Right? Particles at here, it tries to goes down. But from here onwards, what is the direction of particles now? Is it also trying to goes down? මෙතන චුට්ටක් මේක උඩට හිටිලා තියෙන්නේ. අපි හරලා දෙනවා. Right. So in this region, these particles are now they tries to goes down. But air again, particles at this region they try to close up. We are MCQ direction of particles, right? So what can you say about the direction of the particles of either side of the crestograph? What can you say about direction of motion of the particles at either side of the crestograph? Are they in same direction or in opposite direction? They are opposite. Right? Remember that the direction of particles either side of a crestograph, the opposite. Write that point also. Direction of the particles at either side. Direction of the particles at either side. Direction of particles at either side. And both sides. And both sides. Of a crestograph. Of a crestograph is opposite. Is opposite. So now you can draw this instantaneous wave shape, right? So this is the wave. We can repeat position of the wave after a short while. Right? So this will be very significant when there are I think 3 or 4 MCQs in past papers, right? You have to identify the direction of motions of the particles, right? So you need to know the instantaneous position of the wave and check the direction of the particles. Make a දුන්නට පස්සේ ඔයාලා පොඩ්ඩක් එකකින් පස්සේ wave එක කොහොමද යන්නේ කියලා ඇඳගෙන තමයි direction එක mark කරන්න වෙන්නේ, right? So these arrows indicate the direction of motion. So these are the particles at troughs and crest. I take different colors to it. Right. Right. Next point is distance between the distance between two adjacent crests, both arms is equal to the wavelength of the wave. Right. So what is the distance between two adjacent top and crest, or crest and top? Distance between two adjacent top and the crest. Half of wavelength. Wavelength के भाग में right? So in a transverse wave, a wave shape like this, right? So a wave, we say a full wave cycle to a shape of like this. So this is a full cycle of wave. Make it again a one wave cycle is. This is one wave cycle, right? So length of a one wave cycle is equal to, also equal to wavelength, right? So this is one wave cycle. So it is equal to lambda. The phase difference, right? Phase difference here. Suppose if the phase angle is 0 at here, the particle at here has 2 pi phase angle. So phase difference is 2 pi. Phase angle difference is 2 pi. So you can draw this also. This is known as one wave cycle. This is one wave cycle, and length of the cycle is lambda. Length of a wave cycle is lambda. The next topic is longitudinal waves. Longitudinal waves. Longitudinal waves. Longitudinal waves. Right. So longitudinal waves are waves in which the particles move parallel to the direction of wave travels. In longitudinal waves, particle moves or vibrates direction parallel to the wave travels. Right. So suppose the direction of wave travel is this direction, and particles are vibrates direction parallel to this, right? So particles are move like this. So this is how longitudinal wave propagates, right? So when a longitudinal wave is travel in a medium, like when a longitudinal wave is traveling in a medium, you cannot see crest and troughs like transverse waves. You cannot see the shape of the wave is going there. Right? The surface water wave, you can really see the crest and troughs there. But when a sound wave propagates in the air, you cannot visualize or you can't see the troughs and crest like that. Right? Actually, it can the trough, so longitudinal wave doesn't replicate the graphical shape of the wave. Right? So when a longitudinal wave propagates through medium, at some points, at some regions in a medium, the particles tend to come closer. Right? They confine at some region. At some regions, they actually particles are less dense there. Right? They tend to separate with each other in the long distances. At some places, particles gather together, and right next to the area, particles are together. The opposite side to the adjacent area, the particles are less there, less dense there. Right? So this is how we can find. And suppose this is how a sound wave propagates through a medium. But at some regions, the particles, density of the particles gets high. Right? They confine to a small region. Then, at some regions, the separation between particles are high. Right? And again, there's a region, again, these particles are confined to a small region. The particle density is high. At this region, particle densities are less. And again, there's a region, the particles are at long distances. Right. So this is how a longitudinal wave propagates. Particles at the long period. At some regions, they are at long distances. So what are these regions? Right? What are these regions? The regions where the particles, the density of particles are high. These regions are called compressions. They are compressions. And the regions where the particle density is less, particles are less denser here. These points are called as rarefaction. Rarefactions. So you can't see crest and troughs where longitudinal wave travels, but instead of that, you can identify compressions and rarefactions. Compressions and rarefactions. Particle wave and longitudinal wave can have a medium wave, compressed like a spring does. Spring that again. Particles will combine, I get because of the moving. Particles moving in there, but energy transfer there by moving particles like this. Right? So, in a longitudinal wave, the distance between two adjacent compressions, distance here is equal to lambda. So, distance between two adjacent rarefactions also equal to lambda. Equal to, right? So what is the example? All right, can we example with longitudinal wave, sound wave? I'm getting sound wave. Tied up, as I speak, P waves, primary waves are longitudinal waves. Right? Normally, typical examples of it, right? So how we represent the longitudinal wave in a graphical way. Right? Transverse wave in a graphical way. Right? Topic. Yeah. Yeah. Longitudinal wave, longitudinal wave, longitudinal wave is a wave. Longitudinal wave is a wave in which particles of the medium vibrate parallel to the direction of wave propagation. Direction of wave propagation, right? So draw this like we did to the transverse wave, like this. This is the direction of wave propagation. Take a leaf. Write the examples. Only the about एक पास से लेना एक हम जो आगे तो आगे दिखो उन्होंने किस लेने के लिए like there are examples. Sound waves in air. Then seismic P waves. Seismic P waves. Right. Next paragraph. When a longitudinal wave travels in a medium at some regions particles in the medium get closer. Those regions are called and then compressions. And at some regions, Particles are far apart. At some regions, particles are far apart. Those regions are called rare fractions. Rare fractions. The distance between the distance between two successive compressions. Distance between two successive compressions or two successive rare fractions. Two successive rare fractions is equal to the wavelength is equal to the wavelength. So then the distance between successive rare fraction and compression is equal to lambda by 2. Right? Okay. So you can draw this. So sometimes we now you can draw. So at these regions, particles are very close together. They are at right. So when you sounded that tuning fork, this is what happened in air. When you sound a tuning fork like this, the left arm of the tuning fork vibrates, it produces a sound wave, and it travels like this. So instead of drawing this, you can draw this one. Yes. Huh? Yes. Okay, we can. We just like when you put that on the if you already draw this, only thing you have to draw a tuning fork in front of it. Yeah, draw this. draw both these. Then, so what can you say about the particle density and compressions? High, density is high, and rare fractions, the particle density is low. And also, what can you say about the pressure at compression? Pressure high. Here, pressure is less than the normal, right? Here, at compressions, particle density is high. Particle density and pressure. There. Particle density and pressure is high. At rare fractions, particle density and pressure is low. Right. So how we can see the wave shape? How we graph the longitudinal wave, right? How we represent it graphically? Right. So we have some particles here, and these are particles, right? So at the initial moment, these are some particles. A number in there, 5, 6, 7, 8, 9, 10. Right. And somehow we vibrate these particles, right, using an electrical vibrating source. So somehow we vibrate these particles longitudinally, right? So suppose when you vibrate these particles longitudinally, right? So at near the second particle, there is a compression, which means second particle, which is remain, it keep its position still, right? Suppose we assume this particle 1 has come closer to the particle 2. Then the particle 3 has came closer to the particle 2. Right? 4 is still there. We can assume but I'm not going to draw it. Simplify right? Particle 4 is at rest, right? Now particle 5, right? It has gone closer to fifth one, so sixth particle, and particle 7 has moved to here. Particle 8 is at rest. Like that, particle 10 is at rest, 9 has come closer. Right? 11 there's 11 particle. So now you can identify what are these things. These are compressions, these are rare fractions. Right? So when you graph a longitudinal wave, you cannot draw a graphical or graph by looking at the displacement of the particles and along the direction of motion. Again, when you observe a transverse wave, the wave patterns, you can see, you can visualize it. Wave goes like this. Right? The graphical shape of the wave is also sinusoidal. But for a longitudinal wave, you cannot draw such a shape or wave because it moves like this. It's not sinusoidal. And like a sinusoidal wave. But here, what a hard make a touch it. But we are going to draw a graph with the displacement, right? The displacement done by this particle. The displacement done by this particle represented by y-axis. The displacement done by this particle represented by y-axis, right? And this is the distance to the x-axis. Horizontal direction, right? So this is x-axis. Now see what happens. Right. So what can we say about the displacement of this particle A? Right? Particle A. Right? So what is this displacement of particle A? It is maximum. Because particle A has moved, the maximum distance it can go. They cannot very good. A maximum displacement. The particle 1 maximum displacement. Right. So this is particle 1. Particle 1 right. So what is displacement of particle 2? It is at rest. 2 is at rest. 2 is at rest. So what can you say about particle 3? Yeah, it is maximum. What direction is? If you take the direction positive to the right direction, so particle 3 has moved in the opposite direction. So it is negative. So particle 3 displacement is maximum, but it is negative. Particle 4 is at rest here. Particle 4 is at rest. Particle 5, it has moved the optimum distance. Within the heater. 5 is at here. On particles, what are the points are? By particle 6 is at rest. Particles 7 has gone to the other side. 7 negative method. By 8 is at rest. By 9 has gone to the other side. 9. 10 is at rest. Now I am going to draw these points, join with these points. Right? So now I can get the shape of the transverse wavelengths. So now I can get the wave shape. The wave shape is अब मैं क्या transverse wave एक आप याद नहीं particle लेके vertical displacement पे क्या wave के propagation direction लेकर measure कर length पे काम करना है आप वही shape पे क्या मैं क्या याद नहीं even direction propagation direction लेकर तक तो अपने हिमालय में है मैं याद नहीं we horizontal displacement लेकर तो आप मैं बता ना मैं vertical मैं y axis के represent कर दिए थे horizontal displacement of the particle along the direction of wave traverse. This is what we do. Graphical representation. Graphical representation of. Graphical representation of longitudinal wave. When a longitudinal wave propagates in a medium, when a longitudinal wave propagates in a medium, we cannot see the sinusoidal, we cannot see the sinusoidal, 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 sign function, sinusoidal means how the sign x varies with the x as a sine function. The shape of this is sinusoidal, right? We cannot see the sinusoidal shape of the wave. Sinusoidal shape of the wave. Right? We cannot see the sinusoidal shape of the wave. In order to represent a longitudinal wave, in a graphical way, we plot the distance moved by the particles in the media, from their center of oscillation, against the distance measured towards the wave propagates. Right. Following figure shows positions of the particles when a longitudinal wave travels in a medium. कोई लोग कॉपी कर रहे हैं। Right. Right. Some important quantities. Some important quantities related to some important quantities related to the wave. Okay. Some important quantities related to a wave. Some important quantities related to a wave. Right. First one is the amplitude. Amplitude. Amplitude, capital A. So what is an amplitude? Amplitude is the maximum displacement done by the particle. When a wave propagates in a medium, the maximum displacement of a particle is called amplitude. It is a maximum displacement. Amplitude is measured in meters. Unit is meters. Right? The next term is time period or period of time. Time period. Right? Capital T. So we have defined this time period over in several lessons. Circular motion, pairs, angular motion, the time period, and wave motion. In wave motion, also simple harmonic motion. We talk about time period. So what is the time period in a time period of a wave? Time taken to frame one wave cycle. Time taken to produce one wave cycle. A wave cycle produce time there. Wave cycle is a wave shape like this. Right? Time taken to complete one wave cycle is time period. The time period is given by expression 2 pi over omega. Then the other one is frequency. Frequency of the wave. So what is frequency? How will you define frequency? Number of wave cycles per second. How many wave cycles it creates in a 1 second period of time is the frequency of the wave. Right? Then the wavelength. Wavelength. So we use specific symbols to these quantities. Wavelength. So what is a wavelength? In general, wavelength is the shortest distance between 2 points with phase difference or phase angle difference is 2 pi. Phase angle difference is 2 pi. Distance that points that cover shortest distance. Wavelength is the distance between 2 points where the phase difference is 2 pi. Right? Whenever the phase difference is 2 pi of 2 points, the distance between those 2 points is called wavelength. For a transverse wave, a wavelength is equal to distance between two successive crest or troughs. For a longitudinal wave, wavelength is equal to distance between two successive compressions or reappressions. Actually, the points at compressions, the points at two successive compressions, they have phase difference of 2 pi. 2 pi difference right? So it is so this is the shape of a wave. These points are crested. So this is how the phase angle is varying. At this moment, right? Here at this moment, this particle, right? The vibration energy does not transmit to this particle yet. So it is at rest. This particle is at the verge of moving. පටන් ගන්න අවස්ථාව එක move වෙන්න පොළොව ඉන්න අවස්ථාවේ තියෙන්නේ. So phase angle here is 0. Phase angle 0. या move වෙන්න පටන් ගන්න තැන ඉන්නේ. But phase angle at here, this particle has moved to the optimum displacement. It is at the amplitude. So it has it's a bit more like a simple pendulum. Right? Let's clear this using a simple pendulum. Right? So these are the some positions of simple pendulum. Pendulum at here, first instant. Then it comes to position like here. Then again it comes to the center. Right? Then again it goes to the other side. The phase angle is like this. This particle here is analog to pendulum at this position. No motion there. Motion is not there. Right? So particle at here is bit like a pendulum at here. So what is the phase angle of this particle? It is 90. Phase angle is 90. Radius 5/2. Right? Suppose we have two identical pendulums. One pendulum is at here. The other one we moved up to here. And suddenly we make them oscillate. When this pendulum tries to move here, this one comes to, it tries to come to this position, right? When this pendulum goes to here, this pendulum has come to the center, right? So the phase difference of these two is 5/2. Then opposite motion. Make a head and other. Now, whether you make or anything, I am I thought we particles phase difference. It is 5/2. Again, we have a center of oscillation again. We are in the maximum displacement. We have center of oscillation again. We have maximum displacement. We have pendulums. Not a single pendulum, right? So this is pendulum 1. This is pendulum 2. So we simultaneously make them oscillate. Right? By keeping them in these two positions. The pendulum 1 starts its motion at center of oscillation. Right? In the same time, pendulum 2 starts its motion at here. So what happens is when this pendulum comes to the end of the or the corner of the its path, this has come to center of oscillation. Right? So it has some opposite motion එකකට මෙයා මේ පැත්තෙන් මෙහෙට මෙයා මෙතන මෙයා මෙතට එනකොට මෙයා මෙහෙට. So then we say the phase difference between these two pendulums are 5/2. 5/2. Phase difference is 0 if the two pendulums are like this. Make a minimum. Then the make a important. A third pendulum same motion these two have. When this pendulum comes to this end, this also goes to that end. So phase difference is 0. Understood? So what happens when the phase difference is 180? Phase difference 180 means so if when this pendulum tries to go this direction, this one goes to opposite direction. It goes to opposite direction. Make a main so phase difference is 180. Right? Particle phase difference so this particle is now trying to come to this position. So phase angle here is 5/2. Right? So particle at here, it also try to go to opposite direction. Opposite direction. Opposite direction. So this is phase angle 5. The difference is 5. Phase difference between these two particles is 5. Phase difference of these two particles 5 over 2. Right. So what is the phase difference of particle here and here? Phase difference between these two particles. 5 by 3. This is 90, this is 180. 3 5 over 2, yes, 3 5 over 2. Phase angle here is 3 5 over 2. The phase difference between these two particles is 3 5 over 2. So what is the phase difference between these two? It is 2 5. It is 2 5. Right? And phase angle here of this particle 2 5 plus 5 over 2. So it is negative 2 5 plus 5 over 2 5 5 over 2 5 over 2. That's enough. Right, now take the phase difference between these 2 points. So what is the phase difference of these 2 points? How we get the phase difference? Phase is 5. Phase angle at here is 5. 5 over 2 minus phase angle is 5 over 2. It is 4 5 over 2, which is 2 5. So these are the points which are at crest, 2 successive crests, and the phase difference is 2 5. So distance is equal to lambda. Right? Like that, the phase difference of these 2 points. Method here. May phase difference again. This is 3 5. Right? You must say this is 7 5 over 2 at this point. So phase difference of these 2 points, how we get it? 7 5 over 2 minus, here it is 3 5 over 2. So 4 5 over 2, which is 2 5. So phase difference of 2 particles which are at successive crest photographs is equal to 5. So which is lambda. Right? So the general definition of the common definition of the lambda is the distance between 2 particles where the phase difference is 2 5. For transverse waves, it is a distance between 2 successive crest photographs. For longitudinal waves, it is distance between 2 successive compressions or aberrations. Right? Okay. Then the final. A wave speed. Wave speed. Right, wave speed. So how we define wave speed? Wave speed, distance traveled by wave in a unit time. Right? Distance traveled by a wave in a unit time is a wave length. Sorry, wave speed. Sorry, wave speed. Wave speed. The distance traveled by wave per second is defined as wave speed. So there's a relationship between wave speed and wave length and frequency. I will give it directly. V equals F lambda is the relationship. I'm not going to derive it, right? That is unnecessary. So I will give you the expression directly. So you know this one. V equals F lambda is the expression that gives the relationship between the wave speed, frequency, and lambda. V equals F lambda, very famous one. What is F? F is the frequency of the wave, lambda is the wave length. Right? Okay, so now I'm asking you, so what effect the wave speed depends on what quantities? By looking at this, does the wave speed depends on frequency or wavelength or not? Yes. Is wave speed of a wave depends on its frequency and wavelength? No. Answer is no. So this is only expression. Although wave speed is given by the product of f lambda, keep in mind the speed of a wave does not depend on its frequency or lambda. It only depends on the properties of media, properties of the media, characteristic of the media, like density and bulk modulus, like those things. Right? Somehow the frequency and wavelength, the product of the frequency and wavelength is equal to v. That's a mathematical expression. Only there. Right? So you cannot change the speed of the wave by changing frequency or wavelength. In order to do so, you need to take the media, properties of media. Right? Speed of light in water, right? Or in vacuum, that does not depend on the frequency or lambda. It only depends on the medium. Medium may not depend. When a light wave enters from air to water, its frequency does not change. Frequency is same, but its wavelength get changed due to the properties of the medium. Right? Keep in mind, although v equals f lambda, speed of the wave does not depend on frequency or its wavelength. It's only depend on the properties of medium. That's it, right? Okay. And amplitude. Amplitude. Topic first is amplitude. Right answer. The maximum displacement of a point of a wave, maximum displacement of a point of a wave from its equilibrium position, maximum displacement of a point of a wave from its equilibrium position is known as amplitude. Right. So it's measured in meters. Unit is meters. SI unit is meters, right? Then the time period. Time period. Time taken for complete one wave cycle. One wave cycle is the time period of the wave. So actual time period is also time period equal 1 over f. F is frequency. Time period is 1 over f. Time period of wave is 1 over f. Unit is second. SI unit is seconds. Right. Then the frequency. Frequency a number of complete wave cycles. The number of complete wave cycles for unit time. Unit time is known as frequency. Frequency is equal to 1 over time period. Frequency is equal to 1 over t. Right. Then wavelength. The next topic is wavelength. Wavelength lambda. Symbol is lambda. Right. Wavelength is the shortest distance between two consecutive points on a wave that are in same phase of vibration. Same phase of a vibration. Within bracket, phase difference should be 2 pi. Phase difference is 2 pi. Right. Next topic is speed of the wave. Speed of the wave. Right under it. The distance traveled by a wave. Per unit time. The distance traveled by a wave per unit time is defined as the speed of the wave. So unit is meters per second, right? Speed of the wave is meters per second. Right, then the topic is relationship between wave speed frequency and wavelength. Yeah. The speed of a wave speed of a wave of wavelength lambda and frequency simple f is given by the expression what v equals f lambda, v equal f lambda. Right, star mark again. This equation is only valid for, this equation is only applicable. This equation is only applicable for progressive waves. When the wave progresses through the medium, not for the standing waves. Progressive waves. The next fact is although v equals f lambda equation, gives the speed of the wave, but speed of the wave does not depend on, does not depend on either frequency or wavelength. It only depends on the properties of the medium wave propagate. Okay, to take down the example. Question number 1. See the question number 1. Right. In a wave motion, what is meant by terms wavelength, frequency, and propagation speed of a wave? What is the relationship between these three quantities? V equals F lambda. The radio program is broadcast of wavelength 500 meters and 60 meters. If the frequency of the 500 meters wave is 600 kilohertz, find the velocity of radio waves. So velocity of radio wave is given by the expression V equals F lambda. Frequency is 600, convert it into hertz, times 3. 500 is the wavelength. So answer is 300,000. So 3 times 10 to the power 8 meters per second. So it is speed of light there, right? The frequency of a 60-meter wave, right? So these two waves are same time. Both are radio waves and also electromagnetic waves. Right? So you can use V equals F lambda equation, and the speed of the electromagnetic waves in vacuum is same. That is equal to speed of light. So this is the speed of the wave. Right? Required frequency 60 is the wavelength. So frequency is 300 5 times 10 to the power 6 hertz. 5,000 kilohertz. 5,000 kilohertz. Right, right and follow. Right. Yeah. Then the following graph shows. The following graph shows. Following graph shows a wave produced by a vibrating source of frequency, vibrating source of a frequency of 60 cycles per second. 60 cycles per second. Find Problem number 1, frequency of the wave. Second one, wavelength. Third one, speed of the wave. Fourth, time period of the wave. Right. So here's the graph. Can you see these numbers? Back to this 1.00, 2.00, 3.00, 4.00, 5.00, 600, 7, 8. So here distance measured in millimeters in y-axis, distance in x-axis measured in centimeters. This 3, take a -3. Right, finished. Now then, what is the wavelength of the wave given? Wavelength of frequency. Frequency is 60 equals 60 cycles per second. Source is 60 cycles per second. So here, source again wave cricket frequency is same. Frequency of the wave is same as the frequency of the source that produce the wave. Right? Frequency of the source is 60 cycles per second. So wave have the same frequency. Right? Next is amplitude. Wavelength. So what is the wavelength of this wave? 0.0 r. So wavelength is the length of full cycle. So this counting one cycle is length is 2 centimeters. The wavelength is 2 centimeters. So 0.02 meters. 0.02 meters. So then what is the amplitude? No. No. Then what? Next. Speed. Speed is here. Is in 120 centimeters per second. You can use V equals F lambda. And the frequency is 60. Wavelength is 2 centimeters. So 120 centimeters per second. Or you can say 1.2 meters per second. Is that? Again, 1.2. So finally, time period 1/60. So what is the amplitude of this wave? 3 centimeters, 3 millimeters. 3 millimeters. Right? So what is the maximum speed of a particle of this wave? What is the maximum speed of particle which oscillates? What is the maximum oscillation wave speed of the particle of this wave? Maximum oscillation speed. How are you getting? Maximum speed like a particle. Huh? So what is the expression used to get the maximum speed? So what is the type of what type of motion these particles are undergo? Simple harmonic motion. So what is the maximum speed of simple harmonic motion? V equals maximum speed. V equals A omega. Right? V equals A omega. So amplitude is 3 millimeters. So what is omega? How you get omega? Time period is 1/60. So time period equals 2 pi over omega. So 1/60 equals 2 pi over omega. So omega is 125 radians per second. 125 is 3.14. That is the maximum speed over particle. Right? Right. So then we can have a break now. Right, okay. Break here now. Okay.